Hello and welcome to York Universe, the astronomy and astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. You will now find us wherever podcasts are distributed. I am Paul Mackin, one of our hosts this evening, and I'm joined by Julie Tomei. We are broadcasting live from the Allan Carswell Observatory, located at the Keele campus of York University in Toronto. York Universe broadcasts live every Monday at 9 p.m. local Toronto time, or currently 1 a.m. Tuesday Universal Time at York U Observatory. We're also running concert with our online public viewing, or as we call it, the OPV feed, run by our observatory staff. To navigate to our live show or to find out more about us, please check out our website at yorku.ca/science/observatory and follow the link to our online public viewing chat on YouTube. Any questions or comments you may have on past shows or suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Instagram at the handle at YorkU Observatory or on Facebook at Allan I. Carswell Ob. All of our programs are free, but if you would like to make a donation, and we would certainly appreciate that, please see our website at yorku.ca/science/observatory. We will be monitoring the YouTube chat for questions and post content. Tonight's weather is looking not too bad for observing, and we have staff in the domes which are open, and we will be likely mixing live and archival images on the OPV. So, how are you doing, Julie? How's the weather in your neck of the woods?
Hi, Paul. I'm doing not too bad. And it was really nice here today. I like a good 20-degree day. Birds are singing. I assume now that it's getting darker, the frogs might be singing. So, all good signs of spring.
Yeah, I got to admit, I love spring, and we're going to talk more about the skies at night later in the show, but I've just, at the beginning of the month, you're still getting a lot of rain, and though you get more dark at night, you get more dark skies at night. There are a lot of overcast nights. Now I'm noticing we're getting more clear nights, and yeah, sun rises a little earlier, sun sets a little later, but we're astronomers. We like to stay up into the night.
Yeah. It's certainly easier to get up in the morning when the sun's up a little earlier.
Absolutely. Well, let's get into our show this evening with some space history. So I think you've got a story to tell us. Over to you, Julie.
Yes, let's do it. We'll start by going back to April 27th, 1933, where Carl Jansky makes the first public announcement of his discovery of radio waves coming from the center of our galaxy, and thus starting the field of radio astronomy. It wasn't a quick pickup, and you'll see why in a moment. So at the time, he was working at Bell Telephone Laboratories. He built a directional antenna designed for a frequency of 20.5 megahertz, which is a wavelength of 14.6 meters approximately. The instrument had a diameter of 100 feet or 30 meters, and it was 20 feet tall or about 6 meters tall. It was mounted on a turntable and set on Ford Model T wheels. That way it could be rotated in the azimuthal direction. And because it was a rotating thing, it got nicknamed Jansky's merry-go-round. The intensity of signals were recorded on analog pen and paper system that was in a shed next to the antenna. He recorded data for several months and categorized the static signals into three groups. The first group being nearby thunderstorms, the second group, distant thunderstorms, and the third, a faint static hiss of unknown origin. So obviously that was the curious one that he focused his work on. He spent over a year working on that third type and learning that the location of maximum intensity rose and fell once a day. And so he concluded, oh, this must be coming from the sun. However, after a few more months, the point of the maximum static of the signal had moved away from the position of the sun. He also noticed that it repeated on a cycle of 23 hours and 56 minutes. Didn't quite know what to make of it. He was talking, discussing the problem with an astrophysicist friend of his, Albert Melvin Skellett, who pointed out that 23 hours 56 minutes is the length of a sidereal day, the time it took for fixed astronomical objects, fixed in air quotes, such as a star, to pass in front of the antenna every time the Earth rotated. So from there, Jansky compared the signal with optical astronomical maps and came to a new conclusion that the radiation was coming from the center of the galaxy in the constellation of Sagittarius. So he made this announcement in 1933 at a meeting of the International Scientific Radio Union in Washington, D.C. The discovery was covered even in, non-scientific media. So it was published in the New York Times on May 5th. He also did an interview on a special NBC program on radio sounds from among the stars. The discovery was published in the Proceedings of the Institute of Radio Engineers in October of 33. And Jansky continued his research. If the radiation was from stars, there should also be a signal coming from the sun, but there wasn't, as the sun was in an inactive phase of the solar cycle at the time. So in 1935, he suggested that the signals were produced by interstellar gas, in particular by thermal agitation of charged particles. He wanted to continue his work, but astronomers weren't interested. So his thesis, to go do higher studies. His thesis wasn't supported, so he wasn't able to do that. And Bell Labs couldn't justify the expenditure of continuing research on something that didn't greatly affect transatlantic communication systems, as it was during the Great Depression at the time. There were a few scientists who were interested, but radio astronomy at that point was a dormant field. Mostly because of the economical situation. Even in scientific fields, there was less. It was less likely to get funding for a riskier type of project. His work did later influence the development of radio astronomy after the Second World War. In particular, a gentleman called Grote Reber, who built his own backyard radio telescope, and John D. Klaus, who started a radio observatory at Ohio State University.
Yeah, it's kind of a fascinating story, actually, because it wasn't just the Depression which slowed it down, the economic situation of the Depression. Immediately after that, the war hit, and all the research went into military applications.
Yeah, exactly.
But Bell Labs played a key role in this going forward, because a few years after the war, Penzias and Wilson were building an antenna and amplifier at Bell Labs, and they noticed a certain background noise that they couldn't get rid of. And they just didn't know what to do with it. So eventually they turned it over to the astrophysics community. And there had been this epic battle going on in Europe, Britain primarily, between two kind of well-known astronomers, one established, in fact, he was the Astronomer Royal, and the other one was this up-and-coming astrophysicist slash cosmologist named Stephen Hawking. And Stephen Hawking had basically given some credence to, an expansion model of the universe from a very small point, which the Astronomer Royal, Fred Hoyle, dismissed as a Big Bang, and the name stuck. And Hoyle's comment was, if it's there. We should be able to see something. So you go over to Penzias and Wilson, and they saw something. And that what they saw, and this came out of basically a descendant of this project, was the cosmic background radiation, which is totally fascinating. And that was the first real measurable evidence for a quote unquote Big Bang. So it really shows you how, first of all, economics and geopolitical forces can affect research and funding, but it also shows you that, no research, of any kind really goes unused ultimately. It's really kind of fascinating.
Yeah, it's kind of sad that Jansky didn't really get to see where it all went. He was in his 20s when he was doing this research at Bell Labs, and he died young. He died at 44. Um, so, I mean, I haven't looked at the dates, but I imagine if you're looking at 33 after the war, that's another, 10 years later. He maybe
Yeah,
saw the beginnings of it, um, but
yeah.
didn't get to see where it went. Um, but there are certainly a lot of things named after him now.
That's amazing. You know, the whole history. I mean, radio astronomy has changed our understanding of astronomy, astrophysics, cosmology, and it's an ever growing field. But not long after that, in May 5th, 1961, the Americans were confronting the reality that the Soviets were beating them in the space race because they'd initially launched Sputnik, the first human-made satellite, and then they put a man in orbit around the Earth, Yuri Gagarin, and the United States was under enormous pressure to get a person in space. They'd already announced they wanted to go to the moon. Uh, their orbital rocket, the Atlas, sorry, they hadn't quite announced it. The announcement would come shortly after this. Their orbital rocket, so a rocket that could get a spacecraft into orbit, was not ready. So they launched Allan B. Shepard in a Mercury capsule on a smaller Redstone rocket, and it just went up and down. It didn't go into orbit. It didn't get to orbital velocity. It was a 15-minute suborbital flight, took off from Florida, landed near the Bahamas. Um, but this put the US firmly into the space race to get to the moon first. Ironically, America only came in second on the human launch schedule due to the fact that they were cautious and they'd already completed exactly the same suborbital flight 3 months before Gagarin's orbital flight with a chimpanzee named Ham in an identical Mercury capsule, also launched on a Redstone rocket. So Shepard's mission on Freedom 7 was followed by by a second suborbital flight 2 months later, and then in January of the following year, astronaut John Glenn became the first American to orbit the Earth on Friendship 7, another Mercury capsule, using that Atlas rocket. The Americans were under a lot of pressure to catch up in the space race, and slowly they did. The Russians came first with a human launch and orbit. Then they were first with a spacewalk. The Americans always seemed slightly behind, but then with Gemini 6 and 7, they managed to rendezvous two manned spacecraft. They didn't dock, they just came close to each other. It was one crew in one, and they could wave to the other crew in the other. And it's actually a bit funny because one crew was up there for 2 weeks, and the other was up there for like a day and a half or something. I don't remember the exact time, but it was very short. And if you've ever seen a Gemini spacecraft, it's the size of a phone booth. And imagine two, grown adult males in a box the size of a spacecraft in a spacesuit, not even able to take that off for 2 weeks. Pretty appalling conditions,
Must have been
right?
pretty ripe in there.
Yeah. But and then on Gemini 8, Neil Armstrong and Dave Scott were the first to actually dock two spacecraft. They docked with a robotic spacecraft. But as the space race went on, risks were taken by both sides, and fatalities did occur. But ultimately, America did win the race to the moon in 1969. Now, interesting. Interestingly, of all the original the Mercury 7 astronauts, and there were seven of them, only one walked on the moon. The man who flew that original suborbital flight on Freedom 7 later commanded Apollo 14 and walked on the moon twice during that mission. He's also famed for a very charming stunt before he left the moon. He had taken with him a 6-iron golf club head, and he attached it to a contingency sample rod and sent a golf ball, traveling for miles and miles. It really only went a few meters, but I think the point was made. That club was returned to Earth, and you can see it at the if you like golf, at the U.S. Golf Association Museum in New Jersey. And there's one final note on the Mercury astronauts. There was always speculation of some competitive sentiments between Alan Shepard, the first American in space, and John Glenn, the first American to orbit the Earth. Now, Shepard was the only one to make it to the moon, and Glenn retired from NASA to have a long and distinguished career as a U.S. Senator from Ohio. But then, in 1998, after retiring from the Senate, Glenn returned to NASA and flew on the Space Shuttle Discovery as a mission specialist for 9 days on STS-95. They're both gone now, but Shepard was the oldest person to walk on the moon at the age of 48, and Glenn was the oldest person to fly in space at the age of 77. Oldest to date, that is, because who knows? We just had one astronaut come back from the space station at 70. So, this is a moving target. But it's fascinating because they competed, and that kind of makes sense. They were all military men. It's a very competitive environment. I think one was Navy, one was Marines, so they compete against each other, and it makes a great deal of sense they'd be like that. But they both excelled, and they both set their own kind of very similar records. I love this story, actually.
Yeah, I mean, in the end, all these astronauts did amazing things that most people won't get to do. I do find it interesting that suborbital, 15 minutes up, 15 minutes now down, and like, or in all.
Yeah.
And like people are paying to do that now.
Yeah, yeah. And actually they just had a launch a couple of weeks ago. It was an all women
Yeah, yeah. I was
crew, and
thinking,
and it's
oh,
been poo-pooed as a publicity stunt. But how fundamentally cool is it that people can do that? I mean, I personally don't have the money to afford it, but maybe one day my kids will or something.
yeah. And when you mentioned that John Glenn was the oldest person to fly in space at 77, like I remember that I was finishing high school or starting university at that time. But also like, um, oh my goodness, why is my brain William Shatner
Yes,
is gone
he
up.
went up. He went up. Captain Kirk went up, and he was 90. And you know what he said the hardest part of it was? The hardest part was rehearsing how to evacuate the spacecraft in an emergency, because you had to be able to climb a certain number of steps in a very short period of time. It's quite a few steps. I don't remember the numbers, but at 90, that was pretty exhausting for him. So,
I imagine so. I've heard him talk about his experiences there, and it just sounds like it was amazing. But I'd have to look up the details. I don't remember. I guess it was a suborbital flight or something like that.
yeah,
Um,
it was exactly the same flight profile as the one that
yeah,
just happened with Katy Perry.
yeah. So
So,
John Glenn gets to hold on to his record a little longer because he went into space proper.
yeah, because he orbited. He orbited, and he did it twice. Once when he was in his 30s, and once when he was in his 70s.
Mhm.
Anyway, so I think you've got another story to tell us about something in history.
I do. So we were in May of 61. We're going to go back a little bit, 10 years. May 3rd of 1951, Gibor Basri was born. Gibor is an American astrophysicist and now a professor emeritus in the astronomy department at UC Berkeley. And he was also the founding vice chancellor of equity and inclusion at UC Berkeley. Usually, when we do these birthday shout outs, the people we're talking about are no longer around, but Gibor Basri is still with us, which is great. So happy birthday, Gibor Basri. His research interests include stellar magnetic activity, star formation, and low mass stars and brown dwarfs. He was born in New York City and raised in Fort Collins, Colorado. His father, Saul Basri, it was an Iraqi Jew and grew up in Basra and Baghdad before moving to the US in 1944. Initially, he was at MIT and became a professor of physics at the University of Colorado. His mother was Phyllis Basri, and she was a Jamaican teacher of modern dance and ballet. She went to New York just before World War II to study dance. And Saul and Phyllis had two children, Gibor and his younger brother, David. The family spent short periods in Burma in 1957 and Sri Lanka in 1965. Experiences that Gibor credits with giving him a broader sense of the world. Basri earned a degree in physics from Stanford University in 1973. He married Jessica Breutman, who is a psychoanalyst and learning disability specialist. They married in 1974. He earned his PhD in astrophysics at the University of Colorado in 79. His thesis was on radiative transfer theory and stellar activity, partially based on observations by the International Ultraviolet Explorer. He did postdoctoral work at UC Berkeley, where he joined the faculty of the astronomy department in 82 and became a full professor in 94. And he remained there until his retirement in 2015 and remains active as an emeritus professor. His work in the 1980s focused on star formation, T-Tauri stars, as well as continuing studies of the stellar magnetic activity, which he'd started in the 70s. In the 90s, he became an early pioneer and world expert in the study of brown dwarfs, inventing a method of lithium dating that revised the ages of young clusters upward of 50% or more. He became a co-investigator on the Kepler mission in the 2000s, using the precision light curves for large numbers of stars to study the behavior of star spots and learn about stellar magnetic activity. He was involved in science education and throughout his career has worked on encouraging the participation of minorities in science. As the founding vice chancellor for equity and inclusion at the UC Berkeley campus, he led the campus to a strategic plan for equity and inclusion, played a key role in a number of climate surveys, and brought diversity considerations to a stronger role in hiring and search practices, advancement and retention practices, and programmatic review for the campus. He's won a number of awards for his research and his education activities, and seems like a really interesting astronomer that I hadn't heard of till this point.
Well, it's remarkable. I mean, this is an incredible career. And I mean, as you were going through it all, I was thinking on points I wanted to touch upon. And, I mean, let's go through a few. I mean, the Kepler mission was one of the most successful missions, in space astronomy. And it was used to look for, exoplanets by looking at one patch of the sky continuously using a planetary occultation method, where these very tiny planets compared to these very pinpoint stars the planets move in front of it and the star dims incredibly slightly. And you would look, Kepler would look at this one vast swath of the sky. And I think it found well over 2,000 exoplanets. And the data, they're still combing the data and finding more. And then there was an extended mission where they did some more of that, I think. And it was an incredible mission. The other 2 points that I wanted to comment on is, when he started looking at low mass stars, we didn't really understand. How prevalent they were compared to others. I mean, we had some idea, but that is most of the stars in the observable universe, I guess. And the good news is they live a really long time. Like our sun's good for 10 billion years. We're about halfway through it, but these stars can go, 100 times longer than that, possibly. I mean, certainly 10 times longer than that. And they are, because there are so many of them, and because they stick around so long, and they seem to have exoplanets. A lot of them seem to have exoplanets. They are actually relatively good candidates for looking for life. Now, on the downside, they also are very active stars. They have very active surface, so they kick off a lot of X-rays, which might have a tendency to sterilize any planets near them. But, we're still learning a lot about this. The other thing is brown dwarfs. I mean, take Jupiter, make it a lot bigger, and you get another star. But there's a middle ground there where a planet is still radiating a fair bit of heat, but not from a thermonuclear reaction at its core. And they're hard to detect, but they also, are out there and they should be detectable because they give off heat by their infrared signature. This guy's worked on just some of the most amazing areas of science, of astronomy. It's incredible. And I hadn't heard of him either. How did you come across him?
I have over the years of doing this show and trying to find new things to talk about in the history section. I found a document that is actually not very long. It's only 3 pages long. But it has sort of like highlights of people and events in astronomy history. And so I kind of like pick one out of there every now and again. Um, it's sad because like one of my best sources for history topics disappeared recently.
Oh.
Yeah, I know. It's like, oh, um, it hadn't been updated in a while, and then just phew, disappeared from that section of the NASA
Yeah,
online universe.
it's challenging because it does take a lot of research to put these shows together. That's something I've discovered over the time I've been involved, and it's happy work. But this podcast is done a lot by students, or alumni or graduate students, and it takes effort. And again, the observatory is a volunteer organization. It's run by volunteers, and we do this out of passion and love. And that's one of the nice things about astronomy, in my opinion. You can be a professional, and several of us are working to that, but it is one of it is one of the sciences that is the friendliest to amateurs, and where amateurs can still make a real contribution to the body of knowledge. But it's I've developed a real appreciation for how hard it is to do something like this and put this together every week, and the amount of research that goes into it is a bit inspiring. So thank you for looking that up, because I was wowed when I read that earlier.
Yeah, no problem. I also like that when I come across some of these like lesser known astronomers, they're not all old white guys that lived in Europe hundreds of years ago. Um,
Yeah.
and B, some of the stuff is things that kind of overlaps with my own studies, right? Like I started at York in the late 90s, like this whole like Kepler. I mean, John Caldwell from York, longtime professor at York, was on the Kepler team. One of my friends did summer work study work for him on the Kepler mission before it launched. The other thing I find interesting about this is that like Kepler's primary mission was find planets. And here, Dr. Basri used the data to study the stars themselves because there's just so much data that came out of that mission.
Yeah, you're absolutely right. And one of the things about collecting data, I worked on a project in the 1990s where we were collecting a lot of. It wasn't astronomy; it was remote sensing for Earth sciences. But the amount of data even then we were collecting, one of the biggest challenges was the amount of storage you required to have that data. But it could all be mined continuously, and we're still doing that. And we're getting more and more and more. And with some of the instruments that are coming online, that's going to go right through the roof. But we're now at the halfway point of our show, so I've got a couple of reminders that I have to read out here. So you are listening to York Universe, and we're broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. Please look at our website at yorku.ca/science/observatory to join the chat, which is going on now with our online public viewing, and there's some wonderful live images right from our telescope on the OPV right now. And you can type in questions if you want to see some of our content. Tonight you're listening to Julie Tomei and myself, Paul Mackin. We've been discussing some historical items. So again, and if you want to see the OPV, please take a look. It's a lot of fun. And right now you can see, weather conditions, and you can see the domes open, and there's images. It's fantastic. As in the case most weeks, we'll be hosting a live tour of the observatory on this Wednesday. Tickets are free and can be found on the website to get them. And of course, donations are always welcome. We also, for the observatory tours, have a little table where we sell some swag, some t-shirts and shopping bags and calendars and things. And that also, those very nice items also go to help support the work of the observatory, which, as I mentioned, is a volunteer organization. Alternate weeks, we mix up those viewing events on the instead of going to the observatory, we go to the fifth floor of the Arboretum Garage, which is just across an alleyway from the observatory. And in those events, weather permitting, we'll look at some celestial objects rather than through a computer screen, which is what we do with our larger instruments, through a number of telescopes. We've got 5 or 6 scopes up there, and we alternate between observatory tours and star nights at the Arboretum on a weekly basis. Again, weather permitting over the spring and summer months. Okay, so let's move on now to news. And on Easter, on April 20th, the Lucy spacecraft flew by asteroid Donald Johnson. This was the second asteroid flyby of its 12-year mission to observe the Jovian Trojan asteroids, and I'll explain what those are in a minute. But Lucy was launched in October 2021, and then a year later went around the sun, pretty close to Earth, but slightly outside of Earth. A year later, it came back really close to Earth and picked up a gravity assist from the Earth. It captured a little of Earth's momentum, and Earth lost a little bit momentum because that's physics, before heading out to fly by asteroid Dinkinish. I think I've got Dinkin-ish, yes, in 2023. Now, asteroid Dinkinish was really interesting because as they got close, they had some evidence that it had a moon. Two asteroids going around each other, and they got close to it. They could see that the moon actually was 2 asteroids that were split apart and then joined together. They were called a contact binary. So it was a very complicated little system. Anyway, after they flew by asteroid Dinganish, they then returned to Earth for another gravity assist in 2024, which put it on course for Jupiter's leading Trojan asteroids, and Donald Johnson was on the way. It was a flyby on the way. So the flyby at 960 kilometers was quite close as such things are measured, and the data is coming in over the next couple of weeks. That being said, you can see the images online. Just look up Donald Johnson, one word, no space, flyby, and you'll see the images. But they're quite impressive, showing an elongated peanut-shaped asteroid, which is about 8 kilometers long and about 3.5 kilometers wide at its widest point. Now, the Lucy mission and Donald Johnson and Dinkinish have an interesting name convention. Lucy, also named Dinkinish, refers to the fossilized remains of a female, I'm going to get this totally wrong because paleontology is not my thing, Australopithecus afarensis hominid. I'm sorry to all
It's
my
okay. I have,
paleontology friends.
I do know these words, so I got you.
All right, well, what are they?
Australopithecus
Yeah,
afarensis.
outstanding. I'm glad one of us knows what they're talking about. Anyway, this is hominin. Um, and while not likely a direct ancestor, it's been reported in the press as a direct ancestor of modern humans. She was definitely walking along the same evolutionary path, upright that is. She was an upright walking.
Quasi.
Yeah, she could walk on her hand or on her hind legs, and that was definitely on the same evolutionary path as us. Now, Donald Johnson was the paleontologist who discovered her.
Oh,
And this is all related to the Lucy mission, as the Jupiter Trojan asteroids are candidates for sort of the fossilized remains of the early solar system,
I
which
love it
means
so
that
much.
which Lucy is a space paleontology mission as much as anything else. Now, the Lucy mission itself is really kind of amazing. Trojans are asteroids grouped ahead of or behind a planet, and they're held there in a gravitational dance between the planet and the sun, and these Lagrange points, one in front and one back. Okay. Um, and Jupiter, being a really large planet, has a lot of these asteroids in front of it. Okay, so after visiting these two first asteroids, which are not Jupiter Trojans, it'll head out to about 60 degrees ahead of Jupiter in its orbit and fly by four, or possibly five, as one might be a binary, of these objects in 2027 and 2028. And then it flies all the way back across the solar system, goes by Earth for another gravity assist, and heads back towards Jupiter, but this time 60 degrees behind it in orbit. To fly by a binary pair of asteroids in the trailing Trojans. So all told, Lucy will visit 5 or 6 Trojans, 2 standalone asteroids, and perform 3 flybys of the Earth over a 12-year mission. And then we start to look at options for an extended mission. It's just a fantastic story of science and discovery.
When I first started reading your show notes, I was like, why is this not ringing a bell? Why do I not know of the Lucy? And then you said that it was launched in October 2021. I was like, oh yeah, I was kind of busy with other things.
Yeah, it's incredible. There's actually a lot of interest in asteroid missions right now. First of all, there's a planetary defense aspect to it. We've recently fired an asteroid, fired an impactor at an asteroid, and Didymos, and it was 2 asteroids, one orbiting the other, which is actually more common than people might imagine. And we wanted to see if the smaller one orbiting the larger one, they actually both orbit a common center of gravity, but that's a quibble at this point. it hits it, hitting it, they wanted to see if it would slow it down and thus move its orbit a little closer to the common center of
Hmm.
gravity. And it did. It was very successful. It was more successful than we imagined. And the Europeans, as a follow-up mission, are sending a mission called Hera to go and look at that now and see how it's all shaped out a couple of years later. There's another mission called Psyche, which is on its way to an asteroid which is metal. And one of the reasons that's interesting is it might be, first of all, it might be the core of a failed planet, which is amazing in its own right, but it's also because it's metal, there may be, space mining opportunities. There are commercial interests that may come in there. And then there's this space paleontology mission, which I find fascinating. And then in a minute, you're going to talk about the New Horizons spacecraft. That also has, and I'll talk about it after you finish that bit, some implications or some after effects that are also kind of asteroid-like. So we're very, very interested in asteroids. There's a lot of them in the solar system. They can hurt us. They can also benefit us, and they can tell us a lot about the formation of our solar system. It really is fantastic what we're doing now.
Yeah. Um, I I just can't get over the name of this mission. It's so good.
Yeah. So please tell us about the New Horizons observations.
I will. Okay. So we've talked about one mission whose data was used for other things. We've talked about another mission that may have some, extended missions afterwards. Here's another example. So New Horizons observations lead to the first Lyman alpha map of the galaxy. And I did a bit of a double take when I read the headline because I was like New Horizons that went to Pluto. Like, there's no other New Horizons, right? Yeah, New Horizons that went to Pluto. So, New Horizons was the spacecraft. The original mission was a flyby of Pluto back in 2015. During its initial trip, it collected baseline data about Lyman alpha emissions with the ALICE instrument, which is a far UV spectrograph. Lyman alpha is the name given to a particular wavelength of radiation that's emitted and scattered by hydrogen atoms and is useful in the study of distant stars and galaxies, the interstellar medium. And this is because it can help in the detection of their composition and temperature and movement. The mission completed its primary objectives, after which the ALICE instrument was used to make further observations, this time broader and more frequent as the spacecraft traveled further from the sun and onto its next target. In 2023, more than 83% of the sky was mapped. And the results of this have been published by R.G. Gladstone and his co-authors in the Astronomical Journal in an article entitled The Lyman Alpha Sky as Observed by New Horizons at 57 Astronomical Units. This is the first map of the galaxy at this wavelength, and it gives new perspectives on the regions surrounding our solar system. The team had to model scattered solar Lyman alpha radiation in order to subtract it from the data. And the result is a roughly uniform background radiation, about 10 times stronger than expected. So what conclusions have these astronomers drawn? The hot interstellar gas bubbles, like the one our solar system is embedded in or within, may actually be regions of enhanced hydrogen gas emissions at the Lyman alpha wavelength. Emission and scattering of Lyman alpha protons by hydrogen atom in the shell of a hot bubble known to surround our solar system and nearby stars was formed by a nearby supernova event a few million years ago, were studied. And the scientists at one point had theorized that there's a wall of interstellar hydrogen atoms, or that, yeah, that would there's a wall at the edge of the heliosphere, the vast region of space dominated by solar wind, as it interacts with the interstellar medium. The theory was, or the idea was, that at that point there would be an accumulation of hydrogen atoms. However, the study found no evidence of this, or if it is there, it's not contributing to the Lyman alpha radiation. But it seems to suggest that it's not there. Um, and this research is giving a new view of the area around our sun. It's revealing new characteristics and challenging older ideas, and is the start for more research that will hopefully reveal more things.
This reminds me that one of the things that happens when you build spacecraft is they have to be over-engineered because for a couple of reasons. Number one, space is a really harsh environment.
Mm-hmm.
It's very hot, very cold. There's high levels of radiation, cosmic rays. The further you get away from Earth, the worse that gets. And so we over-engineer spacecraft, but we also put scientific instruments on them. And when a primary mission ends, there's always a search for an extended mission. And it could be just doing more of the same. For example, the Juno spacecraft orbiting Jupiter was primarily interested in Juno's magnosphere. Once that mission was over, then it started concentrating on the moons of Jupiter, taking images and so on, and getting information on their magnetic fields and their reaction to Jupiter's magnetic field. This is a classic example of this. Someone using an instrument that wasn't going to be used for after the primary mission, very likely, and mapping out, developing a map with it. That's incredible. What a great story. The other thing about this mission, though, is that, of course, after the New Horizons mission was over, and this comes back to our story about asteroids, and this is not technically an asteroid, because asteroids are the objects. They're small rocky objects, bet generally between the orbits of Mars and Jupiter. Although they can come in certainly closer than that, and they can certainly go out further. But then when you get outside of the orbit of Neptune, Pluto is definitely an example of this. You're getting into the Kuiper belt. And those are more icy objects in sort of a shell around the solar system, and sort of a disk around the solar system. And then New Horizons went and visited one of those and produced some great images. And again, this is me mangling names, but it's Arakoth. And it's, again, if you saw a picture of Donald Johnson, you would see it as quite similar to Arakoth. It's kind of peanut shaped, but Arakoth is reddish, mainly because it's made of methane ices and so on. But it's kind of fascinating that that mission has done all this extra work and it's still going. And it was launched, I think, in 2006, so nearly 20 years ago, January 2026. Carried out its primary mission by 2014. Did a secondary mission, I think, by 2019, and now it's still going, but it's doing other things. And they might, if they can get the funding and if they can find an appropriate target within their fuel budget, they might be able to get one more Kuiper Belt object in there. And I don't even want to talk about, what's outside the Kuiper Belt. There's the Oort cloud, which is an entirely different beastie, but maybe we'll talk about that another day. But isn't it amazing how much work they're able to get out of these very expensive spacecraft? But when you think about what they do and how long they do it, they're totally worth the money. And the Voyagers are still going. What, 50 years later, coming up on 60 years later? It's incredible, isn't it?
Yeah, it's amazing. Um, it just it's also amazing what you can do with the different things you can do with a data set.
Yeah, absolutely. Absolutely. The data is sitting there and it may have been used for one purpose and used well. but then suddenly you go back and look at it and there's some other piece of information in there that you wanted. So it's just totally fascinating. And we're collecting so much of it. We're collecting so much of it. And this is, back to a point I made earlier. A lot of it is publicly available. And that's the world where citizen scientists, citizen astronomers can play a part in discovery. So it's incredible. And speaking of citizen scientists and observers, let's take a little bit. I want to introduce us doing a bit on the sky at night, because as we're going changing seasons, I was remembering, and I was feeling a bit glum towards the end of April because I couldn't get my telescope out. It was raining every night, and then my wife reminded me of that old song, and I think it's though April showers may come your way, they bring the flowers that bloom in May. And as we go into May, the days are getting longer. We'll have fewer cloudy nights. We're heading towards full spring and summer. And while the nights are shorter, there's lots of opportunities for great observation ahead. But in the meantime, we should get some nights where there are opportunities to look up and see the universe in all its glory. So last night, I was out with one of my telescopes photographing M13, the great globular cluster in Hercules, and it made me think about the fact that this is kind of a spring and summer object that you can take a look at, and it's marvelous to look at, even with binoculars as we head into summer. And summer's a great time to look at star clusters. These are regions of space where stars might be born from the same cloud of glass or clumped together by gravity. They can be loosely bound together, called open clusters, which don't really have a shape per se. And those are, those are just sort of amorphous, or you can get these very tight balls of stars, which are called globular clusters. And globular clusters are generally older than open clusters and are usually situated outside the galaxy in the galactic halos. And it's not just our galaxy that has them. We can see them in other galaxies as well. Whereas open clusters are, the ones we see are located within our galaxy. And I'm trying to think of there's a lot of them, and several of the Perseid double cluster comes to mind. But a very famous one is the Pleiades, which is a winter open cluster. My grandfather, who was the one that got me into astronomy, used to call it the Seven Sisters. And if you ever see a Subaru car, that's the symbol of just seven little stars.
Yeah.
But that's your classic open cluster, and you can look at it and see filaments of gas because the stars are still being born in it. But globular clusters are really fascinating because they're older and they're a little yellower and or redder because they're older stars and so on, and the young stars have burned themselves out. So it's the G type through the M type stars that are still in there. Now, so definitely worth looking at. Now, in terms of planets, Jupiter is quite high in the western sky at sunset, and Mars is near the zenith, so looking straight up at the same time. And Jupiter always makes a great target for binoculars or a small telescope. It's easy to see some or all of the Galilean moons, and you can see them all, but sometimes they're behind the planet or in front of the planet, and you can't see them. Mars, not nearly as impressive. I always say that if you want to just drag your telescope out on the street and impress people, and I've done this, show them the moon, show them Jupiter, show them Saturn. Everyone wants to see Mars, but Mars is kind of, smaller. It's not very big as a planet. It's half the size of Earth. And you'll need a telescope to make out the disk. But even with a modest instrument, you might just be able to make out the polar caps. This week as well, the moon, we just had the new moon. I think we're just having the new moon now. So the moon will be a crescent in the west at sunset and will rise higher in the sky with a greater percentage of its surface illuminated each night. And the moon is always wonderful to look at. And it just even with even with your naked eye, just watching its change of phase every night. It's just so pretty. And through a telescope, you can identify objects and you can see the shadows of mountains. It's just fantastic to look at. Now, if you're an early riser, you can get up in the morning before sunrise, and you'll see Venus and Saturn visible just before dawn. Now, Saturn is a bit unusual right now because it's nearly edge on to us, so the rings are effectively invisible. This happens every 13 or 14 years. In fact, if you are lucky enough to own a copy of the Allan Carswell Observatory calendar for 2025, we have a comparative image of the two, showing them with the rings at maximum view and nearing minimum view, and it's quite dramatic to see. So this happens every 13 or 14 years, and I can tell you that to seasoned planetary observers, seeing Saturn without his rings is it's almost disconcerting. It's kind of like an anemic Jupiter, and you can only see one moon, which is Titan. Uh, but then you think about it, and it's so beautiful when you can see the rings. It's really kind of amazing. Now, Venus, you can't miss it. If you get up in the morning and you've got a clear eastern horizon, it will be the brightest thing you see before the sun comes up. It's dazzlingly bright. And if you look at in a small telescope, you're going to see phases, just like the moon. Finally, we're nearing the solar maximum. And this is a phenomenon which occurs every 11 years. And if you look at the sun through a small telescope with a filter, and that's really important because looking at the sun, even with your naked eye, will damage your eye. So, you need to take precautions and be safe. But looking at the sun, you should see a lot of solar sunspots right now. If you've got the right gear or know someone that does, you will be able to see some prominences and whatnot. But because every 11 years we get a lot of material thrown off the sun, auroras become more common. And right now, we're still in a period where you could see a lot of aurora, even though the nights are getting shorter. Generally, you'll hear announcements about possible opportunities to observe aurora or on the news or weather broadcasts online. So there's lots of opportunities to see things, and astronomy is best by doing it. And another way to do it is to come out and visit our tours. You'll get to see stuff that will amaze you. Um, Julie, do you have anything special you like to look at in the spring and summer?
I have to say that I don't I don't get as much opportunity to observe as I once did, like when I was staff at the observatory. Um, then I was looking at things all the time, and I remember showing people Venus and talking about the phases and looking at all these wonderful things. Um, I mean, for the last 3 years, have been going up to Killarney as the astronomer in residence, which gives me a nice solid week of having a telescope right out the door of the apartment, which is great. Uh, I the Ring Nebula has been a favorite of mine for a long time. Um, the planets are lovely. The moon, so
Yeah.
long as it's not full, I find it too bright to look at through the telescope, anyways.
Yeah, and with the moon, if it's full, you don't
Oh,
get any shadows, so
yeah.
you
You're
really
also
can't see as
blinding
much
yourself.
detail.
Like,
Yeah, yeah, absolutely.
it's bright. Um, but I do make a point of looking up whenever I go outside. And mostly it ends up being like, oh, there's a planet, there's a constellation, there's the moon.
Yeah,
Um,
it's
yeah.
Yeah, it's a joyous thing. But I'm looking out my window and I'm seeing that the sky still looks clear from what I can tell where I am. So as soon as I finish this podcast, I'm gonna drag my telescope outside and go see if I can look at M13. So on that, I see we're at time, and you have been listening to York University Astronomy and Astrophysics podcast, written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Julie Tomei and myself, Paul Mackin. This podcast and past episodes are available wherever podcasts are distributed. You can always connect with us on Instagram with the handle at YorkU Observatory or on Facebook at Allan I Carswell Ob. The website is yorku.ca/science/observatory, and we have a lot of interesting content. And if you feel so inclined, I'm trolling for money again. It's a great place to make a donation to our student-operated, not-for-profit observatory. Thanks for tuning in this evening. We wish you clear skies and good night.
Good night.